Hi folks, we're going to take a look at page 570, number 12. So they're telling us that a spherical balloon is being filled with helium at a rate of 8 centimeters cubed per second, and they want to know the rate at which the radius is increasing given this information. So we'll take a look at the information later on. But I just want to first say that I recognize this as being a related rates problem because I'm looking for the rate of one value given the rate of another value. Okay, as opposed to being an optimization question where I'm looking for a max, a min, some optimal value. So if you don't see anything about looking for a maximum or a minimum, you're not working with an optimization problem. Okay, so let's start by trying to find the related rates equation. So we're relating volume because we're filling up the balloon with air and radius. So we're going to have to work with the volume formula for a sphere. So that's volume equals 4/3 pi r cubed. And since we're dealing with rate of change with respect to time, I'm going to take the derivative with respect to time of both sides. So dv dt is equal to the derivative with respect to time of the other side of the equation. So 4/3 pi r cubed. Okay, 4/3 pi is just a constant. And so I'm taking the derivative of r cubed with respect to time. So I'm going to have to use the chain rule here. So first take the derivative of r cubed, 3r squared, and then multiply that by the derivative of r with respect to t. Okay, do a little bit of simplifying here. So we're left with 4 pi r squared dr dt. All right, so here's our related rates equation. And we see that along with the two rates, we also have the radius variable in there. Okay, so that's why we need some more information in order to solve this problem. So part A is pretty straightforward because they just give you the radius straight out. Don't forget that they also gave us dv dt. So let's calculate that quickly. So the derivative of volume with respect to time is just 8. By the way, you should always take a look to see that the units are consistent. In this case here, they are. Okay, so that's 8 equals, so 4 pi times 12 squared, and then dr dt. And so we'll calculate that in a second. Let's get our calculator out here. So what do we have? We have 8 divided by 4 times pi times 12 squared. Okay, and that gives us 0.004 approximately. Okay, so 0.004 centimeters per second. Okay. Now in part B, they don't give us the radius directly, but they tell us that the volume is 1,435 centimeters cubed at that particular moment. So we can use the volume formula to determine the radius. Okay, so here first I have to find the radius at which I'm interested in. So here I've got 1435 is equal to 4/3 pi r cubed, and I'm just going to solve for r. So r, so I multiply 3, divide by 4 pi, so it's 3 times 1435 over 4 pi, and I'm going to take the cube root of all that. Okay, and let's calculate r, and then once we have r, we can put it into our related rates equation and find dr dt. Okay, so let's this here. So we've got 3 times 1435 divided by 4 times pi. Okay, and all that to the exponent of 1/3. Just easier than using the cube root button here. Okay, and it looks like we have that'll be 7. We'll just call that 7. Okay, so now we'll input all that along with the other information into our equation here. So we have 8 is equal to 4 pi times 7 squared dr dt. So dr dt is just going to be equal to, okay, so what do we have? We have 4, let's just do it, 8 divided by 4 times pi times 7 squared is 49. And looks like we have 0.01. They're asking us to the nearest 100. So 0.01 centimeters per second. Okay, and lastly in C, well here, this is interesting because they say when the balloon has been filling for 33.5 seconds. Okay, so here, I guess we're going to have to assume that this rate of change for the volume here, 8 centimeters cubed per second, is a constant rate of change. It's the only way we can really solve this. So we can figure out what the volume is after this amount of time. So the volume will just be equal to 33.5 seconds times 8 centimeters cubed per second. All right, so what does that give us? That gives us 33.5 times 8 is 268. Okay. All right, so now we're just going to repeat exactly what we did before. So find the radius, and then once we have the radius, we can input this into the equation. Okay, now while it wasn't specifically said that this rate of change is constant, that's really what we have to assume in order to be able to solve this part of the problem. Okay, so let's go back and do the same thing as before. So 268, so I'm going here, 4/3 pi r cubed, and I'll just repeat what I have there. So r is the cube root of 3 times 268 divided by 4 pi. Okay, and let's calculate that here. Let's try to get so we can see it. So 3 times 268 divided by 4 times pi, and look at my liberal use of brackets, make sure I don't make any mistakes, and then I'm going to take the cube root of that, so exponent 1/3, and we'll just call that 4. Okay, so the radius is 4 centimeters. And so now we can input this to our related rates equation. So we have 8 is equal to 4 pi 4 squared times dr dt. Okay, and so dr dt is just going to be equal to, okay, so what do we have? We have 8 divided by 4 times pi times 4 squared is 16, and 0.04. Okay, so here's 0.04 centimeters per second. All right, so just to recap here, step number 1 was to realize that this was a related rates problem and not an optimization problem. Step number 2 is using, in this case here, your knowledge of measurement, we were able to determine the related rates equation. And then from there, based on the information given, fill out all those unknowns that don't include the one we're actually looking for. Okay, so in this case here, we were given directly the derivative volume with respect to time, and we also needed the radius, which was given in different ways, explicitly, and in other ways in which we had to calculate it. Okay, that's it for this one.